Okay, the purpose of this next series of videos is to walk you through the method of separation of variables as it relates to the one-dimensional heat equation. So what you see here on the screen is step one, which is really the problem setup, and this is what is in section one, step one of exercise one. So I just wanted to touch on a few aspects of the problem setup. So the first thing that I wanted to just really reiterate is we have an initial boundary value problem, or an IBVP. And so we always have to start with our differential equation. So that our PDE right here is the 1D heat equation, which hopefully you are familiar with now from the 3 blue 1 brown series. And then the second line down are our boundary conditions, our BCs. And you notice there are two of them. And there are two of them because we have two derivatives in x. So you need one boundary condition for each derivative. And then we have an initial condition, which there's only one of because we only have a first derivative in time. Okay, so the next thing I wanted to briefly discuss is this f of x that is associated with initial condition. So our initial condition is that when u of x 0, so when x can be anything, but when t is equal to 0 specifically, the temperature, which is our u value, u of xt, u of x0, is equal to f of x. And this should really make sense, just intuitively, because, so imagine we have this long, thin rod here, and what we're doing is, according to the boundary conditions, we're holding the ends, so at x equals 0, and at x equals L, the temperature is equal to 0 at both ends. And so if our initial condition was just 0, then literally nothing would happen, and this would be a very boring problem. So your initial condition needs to be something other than 0, or nothing is actually going to happen. Now, f of x could just be a constant. It could be 100. So where the rod starts out at 100, and then you instantaneously enforce the boundary conditions 0 and 0 on each end. And then what we do is we try and see after a long time what happens, or as time evolves, as time moves towards infinity, what happens to the temperature of the rod. So really this should make physical sense. The next thing I wanted to just touch on is notation. So the partial differential equation, the 1D heat equation, can be written as it's written in the problem statement. It's not a problem. Now, fractions can be cumbersome, especially to typeset. So there are several other ways that you can express this. I'm going to tell you about two of them. So the first one is sort of an extremely simple version. And so basically what happens is all of the derivatives, what you're taking in the derivative with respect to, becomes a subscript. So u sub t is equal to k u x x. So this is a extremely simple, extremely clean version. There's one other notation here where you use the del, but you also use a subscript. So it's a bit of a hybrid. So del sub t u is equal to k del sub x x u. I use the second version, the one I just wrote down with the hybrid version, all throughout my PhD, and I actually really grew to like it. Some of you might like the extreme clean notation version, and some of you just really feel very comfortable with fractions. I don't really care which one you use. I would just ask you to start trying out different notation and then choose one and then stick with it. Okay, so your next job is to look through step 2, and I will meet you on another video when you're done.